Okay. Okay. Hello, everyone. Thank you for joining today. I'm going to talk to you about chaotic fluctuations of superconducting qubits. And without further ado, let's do some basic introduction to the concept of quantum information. So from its classical counterpart, we know that the basic unit of information is the bit, which corresponds to some physical system, which can be either in a state 0 or a state 1. Analogously to the quantum case, we have qubits, and we still want our device to be digital. So basically, we restrict ourselves to, again, have two basic states, a 0 and a 1. But of course, as a quantum system, the qubit is allowed to be in any superposition of those two states. So holding under consideration some global phase invariance of a state and the normalization, we can always write it in this form. By the way, is my pointer showing in your screen?
Yes.
Okay, cool. Right. Yes, we can always write it in this form, which allows us to use some very nice and clear way of thinking geometrically about a qubit as a vector pointing on the unit sphere. This vector, which is defined like this, is called the Bloch vector, and its norm can tell us whether a state is pure or mixed. If it's a pure state, then it's living on top of the sphere, so the norm of the Bloch vector is 1. Otherwise, it can be within the sphere or outside, and we have a mixed state with norm larger or equal or smaller than 1. Right, so with that in mind, we have a qubit now to define, and we want a physical system, we want a Hamiltonian to describe it. So we have a 2-level quantum system, right? So we want basically a 2x2 matrix, which has to be Hermitian. And if we want it to be immediately diagonalized, we have basically just this one option here. So this would be the Hamiltonian of a single qubit. Of course, having just one qubit is kind of boring. We want to build some quantum computer. We need to have several of them, right? So in general, we would have several of these terms contributing. And this would be, in fact, the ideal quantum memory, right? So an array of qubits where we can store our information in. However, this picture is still quite boring. We need to be able to do stuff with these qubits, right? So we need to do logical operations. So what I'm doing pictorially here, right? So we input several qubits and we expect some different outcome. In order for us to be able to do something like this, our qubits should be able to communicate, which basically means we have to introduce some interaction terms. So basically something like this, which is a 2-body term. But of course, in actuality, as soon as you turn on the coupling between qubits, you will unavoidably have 3 body terms, 4 body terms, and whatever. And I can summarize this Hamiltonian here with this notation here. So what I'm writing down here is a summation over possible bit strings of length L. And these exponents of the Pauli Z matrices are basically the digits, the corresponding digits of the bit string B. So there's something fundamentally different between the ideal quantum memory and what we actually have. And that is that for the ideal case, we can initialize our system into some state, and we can guarantee that it will be stationary in some reference frame, while the same cannot be said for this Hamiltonian. An example to understand that, we can think of 2 qubits being coupled with each other, right? Notice that the Hamiltonian is already diagonal in any case, so it's quite trivial obtaining the time evolution of the system, since everything is time independent as well. And once we have the time evolution for some initial state, we can calculate the time-dependent norm of the Bloch vector for one of the qubits, let's say qubit 1 in this case. Right? So if you do this calculation without being too explicit with details, you will get something of this form, right? F being some function which depends only on the initial state, and the same goes for G. But the thing to notice here is our second term here, which has some explicit time dependence, right? And this is the norm of the Bloch vector, which basically quantifies the purity of the state. And since in this scenario here we measure the purity of one of the two qubits, a part of a larger system, this also informs us about the entanglement in the system. So in the case where we would have turned the coupling off, so setting J to 0, you notice that this becomes time independent. So basically, whatever entanglement content the system had in the beginning, it will have the same one throughout the entire evolution of the system. However, as soon as you have even some finite coupling, the entanglement of the system is fluctuating with time. And since entanglement is a basis-independent concept, this verifies what I said earlier about the difference between these two Hamiltonians. Right. So the idea is that we want to deal somehow with these many body terms and introduce this problem to our system. So the strategies, there are two main strategies people follow in order to combat this situation. Let's start with the more simple one on the right. So what we have here is two qubits, and we couple them directly with a Hamiltonian that looks something like this. And basically what we do is we make it so that the coupling is sufficiently smaller than the detuning between those two qubits. This makes these terms quite small and more controllable, but at the same time, it makes logical operations on our qubit last longer, which of course exposes it to a new kind of errors. The other strategy that people have is tunable coupling, which is a scheme which is of this form here. So what we have here is two logical qubits, which are directly connected again, but there is also another channel where they are connected via a control qubit. And the distinction between control qubit and logical qubits being that information is stored only within the logical qubits, and the control qubit is only there to act as a switch, basically, for the coupling. So we have a Hamiltonian of this form, and there are several assumptions that go on in here. First of all is that the couplings of the two logical qubits to our control qubit are dominant over the direct coupling between the qubits. Also, the frequency of the control qubit is the dominant one default in the system. And we are working still in the weak coupling regime. So with all these assumptions, one can do a Schrieffer-Wolff transformation for this Hamiltonian, which is transformation of this form. And basically, you can think of it as a perturbative diagonalization of the Hamiltonian. And after this transformation, we can have our Hamiltonian looking something like this. So what it does, it effectively changes the coupling to something like this, where now the coupling parameter depends on the frequency of the control qubit explicitly. So we have something like this. Furthermore, you can notice that these two terms are going to be negative, and this one is going to be always positive. So there is some frequency for the control qubit where this term can become exactly 0. Right? Of course, this is deceptive, as in it's not really completely canceling out the coupling. It's just that to second order in perturbation theory, this system is effectively decoupled. So in the end, you can go to higher orders and you would not have, it would not be guaranteed that you actually have turned the coupling off. So in both of these cases, at the end of the day, what we end up with is having these many body terms being heavily suppressed in different scales, but still heavily suppressed, but not cancelled completely. So we can kind of summarize both of these situations in something like this. We can look back at our Hamiltonian, and we can say what's perhaps the most idealized version, but still somewhat realistic version of what these many body terms should look like. And we can have a requirement that basically these decay exponentially with the range of correlations, right?
Vaggelis, can I ask a question? Can I interrupt?
Of course, anytime, please.
Thanks. Can you get chaos already for 2 qubits?
Come again?
Can you get any chaotic behavior already for 2 qubits, no matter what coupling you choose?
Chaotic behavior for 2 qubits? No, most likely you would not get chaotic behavior.
At least 3.
Yeah.
Okay, thanks.
I mean, you still have the problem of you still have this problem that I mentioned here earlier, but it's much more controllable. I mean, you can just make this very small and make it irrelevant for the time scales that you care for your operation. At the end of the day, you have some finite time for gate operations that you care about, so you can make the coupling small enough so that it won't be relevant for your time scale. But of course, as the system gets larger, this is going to be much harder to control, and this has to become all the more smaller every time as I scale up.
Thank you.
No problem. Right, so I was here. Yeah, so in this case, with this assumption, what we get is a Hamiltonian, which is known in the literature as the local integrals of motion Hamiltonian of the many-body localized phase. And many-body localization is basically a many-body version of the Anderson localization. Anderson localization is some insulator phase of matter of disordered quantum systems, in which case the eigenstates become exponentially localized in real space around some position. In the many-body case, it's kind of extreme to demand something like that. So the localization is more like a localization on Fock space. So what we can think of this pictorially as basically a localization on this kind of hypercube. So here it's just for 3 qubits and it's 3-dimensional, so I can draw something. But of course, if you have 4 qubits or 5 or whatever, this needs higher dimensions. So the idea of this picture here is that each corner represents some configuration in Fock space, and basically each neighbor side is just distant by 1 excitation. Right, so when we have MBL in our system, we know from literature again that basically there is always going to be some kind of transition to a chaotic phase, even for 1D systems. So what do I mean by chaotic here is basically the contrast of, instead of having exponentially decaying coefficients here, we actually have them all becoming of the same order of magnitude. Or in other words, everything becomes heavily correlated to everything else, and distance does not matter that much. Of course, this is a regime that you definitely do not want to operate your quantum computer in, right? So you have to avoid this at all times. So having all these expectations from the phenomenology of MBL, we want to see, to verify these expectations to some actual physical system, which is relevant for quantum computation. And one prime candidate for such a platform is the transpond qubit arrays. So let's start by saying what I mean by that. So we have a superconducting qubit, which is something that looks like this. Basically, it's a capacitor connected to a superconducting Josephson junction. And the Hamiltonian describing it looks like this. So one term describing the energy of the capacitor in terms of the Cooper pair charge, and one describing the energy of the Josephson junction in terms of the superconducting phase. Now our 2 variables are exactly n and phi, and they are conjugate variables. And basically these are bosonic operators. So even though this is not a true qubit in the sense that it's not a two-level system, but in fact it has infinite levels, the fact of that we have this nonlinearity here in the potential energy actually allows us to have good control of which energy levels the system, though that we have good control so that the system remains in the lowest two energy levels. So we can operate it in a regime that it's effectively like a qubit. And this regime is the Transmon regime when the Josephson energy is much larger than the capacitive energy scale. You can contrast the situation with the pure harmonic oscillator, in which case the energy levels are equidistant. Right, so now that we have our single qubit, again, we want to couple them, and the coupling I will model here is basically capacitive coupling, which ends up with a Hamiltonian of this form. So we assume nearest neighbor coupling only, and no specific boundary conditions. Right, so what we might have noticed here is that the Josephson energies of each qubit is allowed to vary from qubit to qubit. And in fact, this is how we model our disorder in the system. Basically, we have all these Josephson energies centered around some value, let's call it EJ, and then we allow for some Gaussian random fluctuations delta I around that value. So the mean of these fluctuations being 0 and their standard deviation, delta EJ, is what we call the disorder strength. So for the MBL to chaotic transition, the relevant parameter is exactly this thing. So disorder strength over coupling. And as this tends to 0, or which means weak disorder or strong coupling, we approach the chaotic phase. And as this approaches infinity or strong disorder, weak coupling, we are approaching the MBL phase. So now that we have this whole machinery set up, I want to talk about the probes that we use to study this transition for this system. So let's start with level statistics. What I'm showing here is basically the energy spectrum of a zoom in of our energy spectrum of the system that we had before. So these are energy levels which are changing with respect to our coupling strength, starting from 0 up to some higher value here. And the relevant parameter that we are not tracking down is the level spacings of adjacent, the level spacings of energy levels. Right, so even by the naked eye, you might be able to spot a qualitative difference on the left of this plot to the right of this plot. So that make it more distinct for you. So on the left side, what we have is an uncorrelated spectrum, meaning each of the energy levels evolves according to the change of the coupling strength, but completely ignoring the rest of the energy levels. And when we have two states meeting here, what we have is the nature of these crossings are called anti-crossings. Meaning, so if I had such a scenario like what I'm depicting here, we have an energy level 2, which is the top one here, and an energy level 1, the bottom one here. However, if I were tracking the eigenstates, the eigenvectors of this Hamiltonian, I would notice that the eigenvector of the energy level 1 is actually more collinear to the eigenvector of energy level 2 than the one of the energy level 1 after the crossing. So basically the states evolve adiabatically in this case and crossing through each other. For such a case, what we have is, as I said, an uncorrelated spectrum, and therefore the distribution of these level spacings should be a Poissonian. On the right-hand side, we have a very different situation. Right, you might notice these level repulsions here, the states kind of bumping to each other and avoiding each other, which leads to some more correlated eigenstates. And the nature of the crossings here is of avoided crossings. So basically we have the same situation as before, but now the eigenstate changed diabatically. And for such a system, we know from literature, again, that the distribution of the level spacings would be Wigner-Dyson, with this parameter beta here reflecting the symmetries of our system. So for beta equals 1, we have a Gaussian orthogonal ensemble, for 2 unitary ensemble, and for 4 symplectic one. For the system that we are studying, we are in the first case here. And once we've calculated the eigenspectrum of our system, we can obtain the distribution numerically, and basically we then have to compare the obtained distribution to these two. And to do that quantitatively, we employ this Kullbach-Leibler divergence, which is defined like this. And basically it's a comparison between two distributions, P and Q. And you might be able to notice immediately what happens is that when these two distributions are identical, this tends to 0. Otherwise, it takes some value which is determined by normalizations. Right. So moving on to the next probe, we have inverse participation ratio, which is defined like this, and is basically the second moment of a wave function. So we care specifically for the inverse participation ratio of the eigenstates, and we're thinking about the expectations for the two cases. So for the many-body localization case, what we expect is that the components of our eigenvectors are going to be basically 0, except from one position where it's going to be basically 1. So we're thinking of it as fixed around some place. And in that scenario, you can substitute this back to the definition, and you can see that the expectation is that the IPR becomes approximately 1 for localized states. On the other end, approaching the chaotic phase, we know that we approach the chaotic phase as the disorder becomes weaker and weaker from before, if you remember from before. So in the extreme limit of a completely clean system where the disorder strength is 0, what you have is you have translation invariance restored, and therefore the expectation for the eigenstates is that they're going to be block waves. So for our discretized system, of course, this is going to be shown as being the eigenvector being the probabilities being uniformly distributed across the system. So basically, substituting, I have a question. No, okay. Right, so substituting again this expectation in the IPR, we see that in this case, for the delocalized phase, we will have the IPR scaling with 1 over the volume of the system. Of course, for a large enough system, this is practically 0, so we have the IPR ranging between 0 and 1. Finally, and most importantly, we have the Walsh-Hadamard transformation. So this is one measure that we actually came up with. And basically, it's a way of extracting the coefficients of the many-body Hamiltonian using the Hadamard transformation, which is given in this equation here. The main problem one has to deal with in order to use this is we have to have some way of assigning a bit label to each of the energy levels of the system, or at least the energy levels referring to the qubit sector of the system. Right, so how do we do that? When we have the coupling turned off, right, so for t equals 0, and let's say that we wanted the energy of such a state, 0, 1, 0, 1, 1, there is a very clear definition of what that means. It means we want a state with one excitation at sites 2, 4, and 5, and ground states everywhere else. However, as soon as you turn on the coupling, even for a finite value of it, this will no longer make sense, because generally the eigenstates will become superpositions of these configuration states. And after a long enough time, this identification won't make any sense anyways. So the way to resolve this is we can think of this as doing very small steps in changing the coupling strength, right? In which case, for small enough delta t, what you will have is you can obtain all the new eigenvectors. And if we're looking for a specific eigenstate at t equals 0, let's say this one from the example here, from our new eigenvectors, there's going to be only one, which is almost collinear to our old eigenvector, and all the rest of them will be basically orthogonal. And that what we identify then as our new 0, 1, 0, 1, 1 state will be the one which is mostly collinear. And of course, you can then, once you do that for every state, you have an identity for each state after a step delta t. You can repeat that procedure for another step of this size and keep track of the identity of each state for indefinite range of t. Of course, as you keep going towards the chaotic phase, deep inside the chaotic phase, this procedure will stop making sense as well, because then you might start having level repulsions which are much more stronger. And basically, you might have level repulsions between multiple states, and the identification becomes more ambiguous. But we won't go to that regime anyways. All right, so now that we have all the players, let's see what we actually obtain. So on the left, we have phase diagrams. The top one is obtained using the Kullback-Leibler divergence, and the bottom one is obtained from the IPRs over the states. So for the top one, we at the red region, basically we are in the chaotic regime, and in other words, the spectrum obeys a Wigner-Dyson distribution. While on the blue area, we are in the localized regime, and the statistics are Poisson. The white, of course, being the transition in the between them. For the IPR, we draw the line of IPR equals 1/2. So along this line, all of these parameters give us IPR 1/2. Along that line, we have the transition. And what we notice immediately is some huge disparity here on these two predicted transitions areas, which we label the twilight zone. Basically, the problem is that MBL to chaotic transition is still an open problem in some sense. There's quite a lot of stuff that we actually don't know about what is happening along that transition. The leading assumption being that there is some intermediate phase where you have multifractal eigenstates, meaning that your states are not exactly localized around one position, but they might be localized along several different positions across your system. And level repulsions may only occur within specific clusters of energy levels. So it's an intermediate behavior between being fully chaotic and fully MBL, which is what is happening here. I mean, one could argue that it might as well be finite size system effects, but these plots are done here for 10 transmons, where in our simulations we have 10 energy levels per transmon, meaning there you have a Fock space of 10 to the power 10. So there's not much space left to blame finite size system effects for. Right.
Sorry, Vaggelis.
Yeah.
Can you repeat it on the x-axis? What is T?
T is the coupling strength.
And this is what controls the transition, right?
Actually, it's more like a ratio. So let me go back here. Right, so this is the parameter that kind of controls your transition. So yes, one thing is the coupling. Yes, weaker coupling, you're more chaotic. Stronger coupling, no, the other way around. Weaker coupling, you're more MBL. Stronger coupling, you're chaotic. But disorder strength of the system also matters. So you can kind of combat having a higher T by increasing as well your disorder and kind of remaining in the same situation. So these two are competing as to which one will dominate at the end.
And the plots are for 2 qubits? 2 or how many?
No. This, you mean the phase diagram?
Yes.
This is for 10 qubits.
Okay, thanks.
Yeah, but as I said, it's for 10 qubits, but it's not really 10 qubits, right? So it's 10 transmons to be more precise. I mean, of course, you want it to operate in the qubit regime. So if it was qubits, it would be a Fock space of 2 to the power 10 states, right? But the point is that my transmon is inherently bosonic, so I don't have just 2 energy levels. I will have infinite energy levels actually per transmon.
So it's the picture you showed on the right part of the previous slide, let's say, with the let's say 2 copies and the coupling in between, but 10 times that, more or less.
Yes. So basically, yes, exactly. You have 10 of these squares, let's so to speak.
And there is only coupling between neighbors.
Exactly. Yes.
Okay.
And no periodic boundary or something like that. Just a chain, basically.
Mm-hmm. And you would say this is 1D?
This is one, yes. This is 1D. Yes.
Okay, thanks.
I mean, the 1D or 2D for systems like that is basically determined by what kind of couplings you have here. So if I would have this, for instance, site 1 coupling to just 1 to 2 more, then you're 1D. If it couples to 4, then you are 2D, 8, 3D, and so on.
Mm-hmm. Okay, thanks.
So it's determined by the connectivity, essentially, of your. Right. Right, so we're done with that. Yes, and on the right side of this, we have the results for the Walsh coefficients. So what I'm plotting on the top right is exactly the Walsh-Hadamard coefficients for 2 different coupling strengths. One which is in the low coupling, weak coupling regime, and one in the strong coupling regime. So what we immediately see is a verification again of the expectation from the MBL phenomenology that these Walsh coefficients are basically exponentially decaying with the range of the interactions, right? So you have this step up here, which is the ideal memory part of the Hamiltonian. Then you have this next step here, which is, terms which describe interactions with distance 1. Then you have distance 2 and 3 and so on. And of course, this hierarchy is going to get washed out eventually as you approach the chaotic regime, right? So they all become basically of the same order of magnitude, essentially, for strong enough coupling. And another way of viewing this is, just for many different coupling strengths, but averaging within Walsh coefficients of the same correlation range. So these are the average of coefficients with correlation range 1, 2, 3, etc. Right, so having established a transition in our physical system from chaotic to MBL, we now want to focus about what possible implications this can have about future designs people have for architectures of such devices. So the one thing is that people actually want to move away from 1D and go into 2D systems. And in fact, we actually did calculations for such small enough systems, but still, I would argue, sufficient to get an outcome. So what we have here, we did again the same phase diagrams. So what I'm having here with C7, S7, etc. So C refers to chain. So C7 is chain with 7 qubits. C9 is a chain of 9 qubits. And accordingly, S7 refers to the surface 7 architecture, which is basically a grid which is of this form. And we have a 3x3 grid also as well. And what we notice, what is denoted here basically, is what you would expect from the MBL phenomenology, that as the dimensionality of the system increases, the MBL phase regime will be receding more and more. And this is in fact what we got. The other strategy people are planning on is basically what is called frequency pattern engineering. So what we have in this scenario is, say we have an array of transmons like this, and what happens is you're trying to make the disorder of your system as much smaller as possible. So ideally fixing your frequencies by demand, and then make a pattern of frequencies of this form. So let's say all sites with gray color being fixed around Josephson energy of 11 gigahertz, and all the red ones fixed around an energy which is of around 14 gigahertz. The problem with this is, even at a conceptual level, that even if you'd go to the extreme case that you have a completely clean system and just this alternating pattern of frequencies, even though you can effectively cancel out the nearest neighbor correlations, what you also do by this virtue is that you increase or amplify the strength of these next nearest neighbor correlations, and so on. But besides of whether this is a valid strategy or not, and in fact there is some regime you can still operate this as a quantum memory, but it's surrounded by chaotic phases. So regardless of that, it still has some rich phenomenology, and it's interesting on its own right from a perspective of NBL phenomenology. So you can look at the spectrum of such a system, which is what I have here, and you can distinguish 4 regions essentially. On the far right, for very weak, for very strong disorder, right, we have full MBL phase. All of the states are localized, and we can think of it as the eigenstates basically being very close to the the zero coupling eigenstates. What happens as we move along is by decreasing the coupling, we come to a second region where the Hilbert space is starting to restructure into some multiplets which reflect some permutation symmetries of the system. And what do I mean by that is, like, if we were tracking something, a state like this, right? In this region, region 2, you will have the dominant contribution being from your free state. However, you also have contributions from all its neighboring states, which are essentially states that arrive from permutations that respect the point symmetries that you have in here. So this one, for this example here, has 2 excitations on sides B, or red sides, and 1 excitation on a gray side, or an A side. Right, so any permutation that still respects this proportionality here is a valid combination, and in fact your eigenstates will be superpositions of such states. Although within region 2 these are still localized, so basically these coefficients will remain much smaller than the leading one. As you move further along into the third region, we zoom in further here, and you start seeing these Lebel repulsions again here and there, and in fact verify with the Kullbach-Leibler divergence that this is chaotic. So what we have is that the system starts to delocalize within these multiplets. So the eigenstate is still of this form, but basically these coefficients now are much larger and more comparable to the dominant one, although this one still remains dominant. And keep going further to even lower disorder, right? You approach the almost clean system essentially. These become almost exactly degenerate, and therefore these become molecular multiplets essentially, reflecting the point symmetries, the point group symmetries of the system. And that's it pretty much. Thank you very much for your time. Let's sum it up basically. Right, so you're going to build a realistic physical system that is going to serve as a quantum memory. You're going to have disorder. That's kind of unavoidable. So as soon as this happens, you might as well make sure that there is enough of it to avoid moving into some chaotic regimes. And even if you do take care of that, you have to be aware that in between your safe zone of operations, being the MBL, and the chaotic regime, which you definitely should avoid, there is some minefield in the between where it might look like you're viable, but in fact is a metastable case of the system that you also would like to avoid. Yeah, and with that, I thank you very much.
Can I ask a question?
Did I pause recording or not?
Same for
No,
me.
still recording.
What?
It's still recording.
No, I said, should I pause it?
Oh. Sorry.
For me, it's fine if we do one round of questions with it, and then we can just have more informal.
Okay, go on.
So maybe I missed it in the beginning because I logged in a bit late. Can you repeat how can I understand disorder? If I understand, I'm asking this because in the last plot that you saw on the right, the x-axis now was the disorder, not the strength of the coupling, right?
Exactly, yes.
So it seemed a bit flipped.
Usually, yeah, we're doing it like that. We are either fixing disorder and varying coupling strength, or we're fixing coupling strength and we're varying disorder.
Okay. So for instance, if you put too much disorder and strong coupling, then you're very close to the MBL regime, as you saw here, right?
Well, if you put both strong disorder and strong coupling, you're in a weird regime, because I don't know where the relevant parameter is this thing here.
The ratio, okay.
Yes, exactly. So one of them has to be dominant to be able to determine whether your system is MBL or chaotic.
Okay, so
comparable, you're probably somewhere close to the transition anyways.
And how do I understand, so to go back to the beginning, how do I understand disorder?
How do you understand disorder? Yeah, basically it's what I have here. So think of it that way, right? So this is just a linear sum of this Hamiltonian multiple times, right? For just different qubits, essentially. So each one of these, you can look at it, these are conjugate variables, right? So n and phi have this commutator. You can think of it as n being a momentum and phi being position. In which case, what is this? This is just the classical pendulum. So you can think of it as each one of these is a classical pendulum. And what you do is you couple them in some weird coupling, if you think about it classically, not so weird if you think about it from electrodynamics perspective. But the key point is what the disorder means. So how I modeled my disorder here is by allowing this Josephson energy here to be randomly fluctuating, right? So I'm introducing some random fluctuations to this thing. So what does that mean is that this term changes, and if I compare it back here to the classical analog, which would be a pendulum, it's like I had multiple pendula where I allow each one of them to have a different length, essentially.
Okay, I see. Thanks. So then, in the plot you have in the second to last slide, on the far right part, then the blue, the lines are basically covering up your space, right? This means that they can cross, and that's how you understand you're in the MBL regime?
No, I mean, you would have to zoom in. Yeah, so basically you would have to zoom in further to get something like this more clear, to resolve better. I mean, they can both cross in the MBL regime, and they can cross, well, they do avoided crossings in the chaotic phase. The difference is how do they cross. So here you have clean-cut anti-crossing, right? You have something like that. The states change in a continuous fashion. In this case, you have these avoided crossings, these level repulsions here, and the states evolve basically in a discontinuous manner, essentially. So crossing is happening in both cases. The difference is as of how this is happening.
So then if you, in that plot again, then if you go all the way to the left.
Yeah,
the
just
fact that
by showing you this, I mean, I cannot convince you somehow. What I
Okay.
can do is I can point you to the Kullback-Leibler divergence. In this same region here, you can see I'm plotting the Kullback-Leibler divergence with respect to Poisson in blue, with respect to Wigner in red. You see that the Poisson tends to 0, which is the identifier. So basically what I mean by that is that if I would zoom in here, in this region, you would see something that looks more like this than like this.
Okay, so then in the same plot all the way to the left, if I understand correctly, you say you're in a chaotic regime or not?
No, that's a weird regime. That's not neither chaotic nor MBL. This is just basically multiplets, right? So like when you have two spins and then you have a singlet and a triplet emerging, this is kind of the situation you have here. This is neither chaotic nor localized.
So it's not a situation where you can say whether it's safe for operation or not.
Basically, yeah, it's irrelevant kind of for I mean, it's also not physical. In practicality, you can never have a real physical system with 0 disorder, right? But yeah, okay, this you can argue of making it arbitrarily small, in which case, yeah, I don't think you still don't want to be in this case. You still don't want to have these degeneracies here, because the problem then is that remember this idea, this concept here. You kind of have to be able to track your state. I mean, in the scheme of having quantum computation, you say I have some state which I have to denote by some bit string, right? So I have to be able to assign an identity to my states. If I am in this situation where these become exactly degenerate, basically, then this no longer has an identity. These are all kind of blended between them. So I cannot pick the state that I want out of all these. I don't have a way of picking out. So let's say if I had alpha 0 being, I don't know, 1/2, AP being also 1/√2, right? So in the configuration where this is 1/√2 plus 1/√2 and 1/√2 minus 1/√2, I have no physical way of figuring one from the other, basically, which is something you don't want. You want all your states to be identifiable. That's kind of where you rely on.
Okay, nice. Thank you.
Problem.
If I get a little bit more on this, on the spectrum,
yeah.
You said that there's an area of the spectrum that the symmetries that your state might be associated with, they get washed out, right?
Yes. Yeah.
Is that a sign of disorder, or
disorder?
How correlated is?
Yeah, disorder is present in all of the calculations here. So whatever I'm showing here is there's always some disorder, which is the expectation of you will have from a real system. So what's happening here, it doesn't have to do with the fact that the system is disordered. Unintuitively, this has to do with the fact that the system is not disordered enough. So you have this washing out here of these Walsh-Hadamard coefficients, which is basically that these many body terms become all equally important, right? So you can think of it that as the system tends to have weaker and weaker disorder, it's much more easy for qubit 1 to communicate with qubit 100.
Yeah.
Right, so this is what's happening here. And it has to do with the fact that you have smaller disorder. If the system fluctuates very heavily, it's actually going to be much harder for qubit 1 to communicate to qubit 100.
I see. Well, what if your state has no symmetries? Then you're not interested in.
You mean,
it doesn't.
What if I go to the clean system with no disorder, but I just don't have it being translationally invariant or something like that?
Well, that's one example. I was referring to the exchange of 1 and 2 in that example of a state that you gave. But yeah, that's interesting what you're saying as well. So maybe we can think about that too.
I'm not sure I got what you suggested.
There was the state that you gave a particular, there in point 2. And you said that it is invariant under the exchange of 1 and 2, right?
1 and 2 being, sure.
Yeah. And you said that this kind of symmetry you see in the spectrum getting washed out. If I understood correctly, that is.
Yeah. The idea is that if in your clean system, this is actually an open problem. I don't have a straightforward answer to you. This is under being researched by a lot of people. So if you do have a system that even in its clean version kind of has some inherent fluctuations of the energies, then in fact it might be that you don't have neither MBL nor chaos. So it might be that then your system is always in this intermediate regime where you have multifractal eigenstates and it's kind of a different beast altogether. But yeah, there is no good answer to your question, unfortunately.
Thanks. A very nice talk.
No problem.
Can I ask a question?
Of course.
No, maybe 2. Okay, nice talk, Vangeli, very nice. More general question, which probably is not so clever. So disorder is usually connected with entropy, isn't it? So do you have a kind of a function that can present, play a role of entropy here in the sense of quantum mechanics, like von Neumann entropy or something like that? And I say that, okay, well, you can answer, but then maybe it's irrelevant, but yeah.
I mean, you could define some kind of entropy. The problem is that there's a lot of entropies here. You can have an entanglement entropy, you can have a Shannon entropy, you can have a whatever entropy, just name it and you put it. So the question is, what is it that you are searching to quantify with that entropy? So are we asking about how strong my disorder is in this system, or what am I looking to answer in that question with that entropy suggesting?
Well, I don't know in general, but I would expect, first of all, to see some evidence for kind of second law here, and then more than that, I mean, the question would be whether you can see some of the evidence of having bounds in entropy. It came to me from the fact that you mentioned special points where some regimes where the disorder becomes almost zero. I was wondering whether using these kind of things you can model at some point, maybe with more sites, some real system and its quantum behavior, which has interesting things.
Yeah, so, just to answer this before you move on, there is a second law of sorts in these studies. So people usually like to calculate entanglement entropy for these systems. And what you in fact will get is essentially, some kind of second law, but it's a different one. So you have 2 ways of entanglement entropy changing. So you can understand them actually by looking. I don't know which one is more useful. Let's pretend it's this one. Yeah, let's say this one. So when you are in the localized regime, right? So you have these coefficients here of the many body interactions being exponentially small. When you are in this regime, you will have, you can expect that for long times, your entropy is going to, your entanglement entropy of the eigenstates is going to fluctuate. And for this exponential case, for this exponential localization, you have the entanglement entropy basically increasing as a logarithm. So it's a logarithmic function of time. On the other hand, if you are in the chaotic regime, entropy is still increasing, but it's increasing ballistically. So basically, it's like a straight line. So what this simply implies for your system is that if you have the actual system, you initialize your system around some location and you allow it to time evolve. What happens in the localized phase is that the entanglement starts to spread logarithmically. So basically, yeah, it has a logarithmic light cone of spreading for entanglement. However, if you are in the chaotic regime, you have a regular linear light cone for your entanglement. So that's some behavior that people are actually aware of and use to probe this this distinction. But yes, in any case, you expect, in both cases, you expect your entanglement entropy to increase. So there is some kind of second law on that.
And is there any measure to connect your disorder with entropy? Is there a function that we can think that connects entropy to disorder so that we can say something?
I mean, the point is that the disorder here is modeled as random noise, right? So in the sense of I have my, the characteristics of my system, and I allow them to fluctuate with the Gaussian distribution around some central value. Of course, what that means is, but when I fix my disorder strength, or basically I'm fixing the variance of the system, it's kind of like I'm in a micro canonical ensemble of Hamiltonians, whatever that means. So I don't know, maybe there is some sense to what you're saying, but I don't know I wouldn't know how to do that.
I'm just
It would be like an entropy defined on a operator space, and I don't know what that means actually.
Well, I just it comes to my mind. It's just an idea. In many quantum systems recently, people talk about bounds in entropy, in particular entropy over some density or some viscosity. And I don't know whether this kind of systems can be used to check this kind of bounds, universal bounds of this kind of quantities. Okay. Maybe there are corresponding bounds or interesting points regarding I don't know, disorder or other entropic-like behavior of the system. But as I say, this is just a general statement. But I have also another even more general question, if you want.
Okay. Yeah, of course.
Okay. The more general question is, okay, this more generic question regarding the subject would be nice to have an idea what is going on. So, can you describe in a few words, the ideal situation, in a sense, what is the aim of trying, to build a quantum computer, and how this kind of works can help us, or actually rule out the building of a quantum computer? Just in a few words, in order to understand exactly what is going on in this field. If you
as to, if I understood the first part of your question correctly, was it to try to motivate why do we care about quantum computers in general?
No, okay. Quantum computers, I suppose we understand.
Okay.
Most well. Okay, we think we understand.
Yeah.
We want to build a quantum system where we can, store information. Okay, I'm saying that because you may correct me.
Yeah.
The way I understand it. So we want to store information in qubits, which are continuous spins.
Yes.
Basically. So okay, so right. So I want to do that, and if I do that, I can expand exponentially my computer power.
Mm-hmm.
So how is this work related to building a quantum computer?
Okay, yeah, that's okay. So the way I'm thinking about this is that there's two parts from people working on quantum information. There's the information part where you are concerned with building algorithms. You might want to do quantum error correction, which is basically, again, an algorithmic sense of protecting your device from whatever quantum noises. And then there's the part of building the actual physical machinery that is going to carry out all these things. So I would characterize this work being in the second category. So the idea being that I want to build a device, right? And I have two, let's say, main functions for it. One is that it should be able to store information, and the other is process it, right? And again, what I did here is all static. It doesn't have to do with time evolution. So I'm talking about the scenario where I am having some static information storing device, which in this case is a quantum information device. So within this cluster of having some device that can store quantum information, I'm arguing that even though people are aware of part of that story, so people are very much aware of those two body terms here, usually they like to pretend like there is no reason to worry about three body terms or four body terms. And that's mostly because the picture is that, yeah, I have some gate operation that involves n qubits, but that's fine because I can always decompose it into single qubit gates and 2 qubit gates. So if I can solve the 2 qubit problem, I'm done. But the idea, what this work is trying to propose here is, no, it's not. This is very much still here. And if you're not being careful about how you set up this device, it might end up being exactly as significant as the two body terms. Mm-hmm. And the idea of how you determined whether you're safe from that or not is about exactly how spread the frequencies of the qubits are versus how strongly they are connected.
Okay, and what would you say to these people who build these memory devices? Can you give them
yes,
a design, a technical design that is useful, or?
Yes. So another thing is, when I talked to this part about the coupling strategies, you have these two here, right? So what I did mostly refer to this case where you have a static fixed coupling. I'm checking different values of it, but in principle, you're not able to change it on the coupling of 2 qubits on demand. So there is this scenario here where people also feel like they can control the coupling on demand, which again, I insist is up to second order perturbation theory. It's not really turning on and off a coupling. But yeah, in any case, I would say that it might be rash to generalize into including this situation as well. So at least for this case, which is actually what IBM is trying to do. And the weird thing that they're trying to do is have the small couplings, but also make this detuning very small. So basically, let me bring you back to this picture. People are actually trying to build this, to build something like this. So they have techniques that they can arrange their qubits like so, right? And they can force their Josephson energies to have very fixed values, right? And they're trying to do this. They're trying to have a very small disorder with a very weak coupling. And what I'm trying to argue is that this is a bad idea for moving on towards the future. This is eventually going to break up miserably if you keep scaling it up. Right, so
nice.
You have to be careful to either bring back more disorder, or if you want to keep this low disorder there, then you have to do something about the coupling.
Very nice, yeah. Good answer. Thank you.
No problem. I'm seeing something in the chat. No, okay. All right, then maybe I can stop recording if there's no more urgent questions. Oh, no, Elias wanted to ask something, or do you want me to stop the recording first?
Yes, I asked. I want to ask. You can stop the recording. It's
okay.
It's okay. It was about Tasso's first question. I have a follow-up question, I guess. So